July the 16th, 1945, 9:23 a.m., British engineer Stanley Hooker stared in utter disbelief at the turbine blade of the German Jumo 004 engine before him. His hands trembled slightly as he held the piece of metal up to the light. The blade was hollow, completely hollow, with a network of microscopic cooling channels inside. At an operating temperature of 1,162 degrees Fahrenheit, 850 degrees Celsius, the material remained stable, precise, indestructible. Hooker, chief engineer at Rolls-Royce, and one of the most brilliant minds in Great Britain, had to admit it. This German turbine was at least 5 years ahead of their own technology. That very evening, he wrote in his technical diary, now archived at the Rolls-Royce Heritage Trust, "We are not developing a new engine. We are copying a German masterpiece." The Jumo 004 wasn't just an engine. It was the world's first mass-produced turbine in history. Developed by a small team of German engineers led by Dr. Anselm Franz at Junkers Motorenbau in Dessau. Between 1940 and 1945, over 5,000 units were built, each delivering 2,000 pounds of thrust, 900 kilograms, with a dry weight of only 1,587 pounds, 720 kilograms. The thrust-to-weight ratio of 1.25:1 was revolutionary. British engines of the time achieved, at best, 0.7:1. The Americans, around 0.65:1. The Jumo 004 made the Messerschmitt Me 262, the fastest fighter plane of the war. With a top speed of 540 miles per hour, 870 kilometers per hour, it effortlessly outpaced every Allied fighter. But the true genius lay beneath the surface, hidden in thousands of engineering decisions, calculations, and innovations that would change aviation forever. When Stanley Hooker and his team began disassembling and analyzing captured Jumo 04 engines in the summer of 1945, they quickly realized the magnitude of the technological shock. Great Britain had been working on its own jet engines during the war, most notably Frank Whittle's Welland and Derwent models. These engines worked, but they were heavy, inefficient, and extremely maintenance-intensive. The Welland delivered 1,700 pounds of thrust, 770 kilograms, at a weight of 1,074 pounds, 850 kilograms. It consumed 1.17 kilograms of fuel per kilogram of thrust per hour, while the German Jumo 004 required only 1.08 kilograms. This difference of 9% sounds marginal, but in practice, it meant an additional 125 miles, 200 kilometers of range, or 15 minutes of extra combat time. More importantly, the British engines used centrifugal compressors, large radial structures that took up a lot of space and increased aerodynamic drag. The Jumo 004, on the other hand, used a revolutionary 8-stage axial compressor, moving air in a straight line through the engine, enabling a sleek, aerodynamic shape. This decision alone reduced frontal drag by 40% compared to British designs. The German development had begun in 1939, when the Reich Aviation Ministry commissioned Junkers Motorenbau to develop a jet engine for the coming jet age. The leadership was taken over by Dr. Anselm Franz, a 34-year-old Austrian engineer with a doctorate in thermodynamics from the Vienna University of Technology. Franz assembled a team of 27 specialist engineers around him. Experts in metallurgy, aerodynamics, thermodynamics, and precision manufacturing. They had a clear goal: to create an engine that delivered 2,000 pounds of thrust, 900 kilograms, weighed under 1,653 pounds, 750 kilograms, and could be produced with the limited materials available to Germany, because, unlike the Allies, Germany had no access to heat-resistant nickel-chromium superalloys in large quantities. Franz and his team had to work with ordinary steel, with temperatures that were actually too low, with precision requirements that seemed impossible. But they had something more important than raw materials. They had German engineering, Prussian precision, and the unwavering will to make the impossible possible. The first breakthrough came in February 1940. Franz's team realized that the key to efficiency lay in the compressor geometry. Traditional designs used wide blades with simple profiles. Franz calculated that thinner blades with complex aerodynamic profiles would compress the airflow much more efficiently. He developed an 8-stage design, with each stage further compressing the air. The first stage rotated at 700 revolutions per minute, compressing the incoming air by a factor of 1.35. The 8th and final stage reached a cumulative compression factor of 3.141, meaning that the air entering the combustion chamber was more than 3 times denser than ambient air. This high compression was crucial for efficiency, but it created a massive problem. The more you compress air, the hotter it becomes. At the exit of the compressor, the air temperature already reached 430 degrees Fahrenheit, 220 degrees Celsius, before any fuel was burned. In the combustion chamber itself, temperatures exploded to over 3,272 degrees Fahrenheit, 1,800 degrees Celsius. The turbine blades directly behind the combustion chamber had to withstand these extreme temperatures while rotating at 9,000 revolutions per minute and simultaneously enduring centrifugal forces of over 10,000 Gs. No material in the world could survive these conditions for long, but Anselm Franz had an idea. The idea was so radical that his own team initially thought he had lost his mind. Franz proposed making the turbine blades hollow, completely hollow. He then wanted to route cold air from the compressor through the inside of the blades to cool them from within. The air would exit through hundreds of tiny holes drilled over the entire blade surface, creating a protective cooling film. His calculations showed that this approach would reduce the effective operating temperature of the blades from deadly 1,562 degrees Fahrenheit, 850 degrees Celsius, to manageable 1,202 degrees, 650 degrees. But the technical challenges were monumental. The blades had to be thin-walled enough to be hollow, but strong enough to withstand the enormous centrifugal forces. The cooling channels inside had to be precisely dimensioned to ensure optimal airflow. The hundreds of cooling holes, each only 0.4 millimeters in diameter, had to be drilled with absolute precision. A single mistake, a single blocked hole, and the entire blade would melt within seconds, and the engine would catastrophically fail. The Franz team spent 18 months perfecting the manufacturing process. They developed special casting processes with ceramic cores that were dissolved after casting, leaving the hollow interiors behind. They invented new high-precision drilling machines, capable of placing those tiny cooling holes with an accuracy of 0.02 millimeters. They tested dozens of steel alloys until they found the optimal blend, chromadium steel, with 13% chromium, 0.5% nickel, and traces of molybdenum. In August 1941, the first complete Jumo 004 engine successfully ran on the test stand. It delivered 890 kilograms of thrust and ran for 12 hours without failure. On July 18, 1942, the Jumo 004 flew for the first time. Mounted beneath the wing of the Messerschmitt Me 262 prototype, the jet age had begun, but the perfection of the Jumo 04 went far beyond the hollow turbine blades. Every aspect of the engine was a masterpiece of German engineering. The combustion chamber used an innovative annular design with 6 separate flame tubes, ensuring even combustion and minimal temperature spikes. The fuel injection nozzles, developed by Bosch, atomized kerosene into microscopic droplets, averaging 15 micrometers in diameter, ensuring complete combustion with minimal soot. The bearing system used high-precision ball bearings from FAG Schweinfurt, lubricated with a special heat-resistant synthetic oil that remained stable at temperatures up to 300 degrees Celsius. The main shaft, connecting the compressor to the turbine, was crafted from a special nickel-chromium alloy, weighing only 28 kilograms, but capable of transmitting 4,500 horsepower at 9,000 revolutions per minute. To put this into perspective, an average car engine transmits about 150 horsepower. The Jumo 04 transmitted 30 times more power. Through a shaft that was thinner than a human arm, the manufacturing precision was astonishing. The compressor blades had to be manufactured with a tolerance of 0.05 millimeters. That's half the thickness of a human hair. The aerodynamic profiles of the blades followed complex mathematical curves, calculated by Franz's team using mechanical calculating machines over thousands of hours. Each of the 8 compressor stages had a different blade design, optimized for the specific pressure and temperature conditions of that stage. The first stage had 19 large blades, measuring 82 millimeters in length. The 8th stage had 76 small blades, each only 12 millimeters long. The entire compressor section was a rotating work of art, comprised of 412 precision-engineered components, each critical to the engine's function. And the most amazing thing was that Junkers could mass-produce all of this. Between 1944 and 1945, an average of 4 completed Jumo 04 engines per day left the factory in Dessau. The quality control was so strict that the failure rate in operation was below 3%, a remarkable figure for such a complex and novel technology. When the first Me-262 fighter planes entered combat in the summer of 1944, Allied pilots were shocked. The reports that came back were almost identical. The German jet was unbelievably fast, accelerating effortlessly out of any situation, overtaking Allied fighters as if they were standing still. An American P-51 Mustang pilot, Lieutenant Chuck Yeager, who would later become the first person to break the sound barrier, wrote in his mission report from November 6, 1944, "I got within 500 yards and opened fire, hits all over the wings. He just accelerated away like I was standing still. I was flat out at 400 miles per hour and he pulled away effortlessly. Whatever engine that Jerry has, it's from another planet." A British Tempest pilot noted after an encounter on January 4, 1945, "Our intelligence told us the Me-262 was fast, but seeing it is something else entirely. It covered 6 miles in the time it took me to turn around. The acceleration is impossible. The engine must be producing double what we were briefed." In fact, the 2 Jumo 04 engines of the Me-262 together produced 1,800 kilograms of thrust. More than the combined engines of 3 Spitfires, Allied intelligence agencies became desperate. In the fall of 1944, the Technical Intelligence Division of the U.S. Air Force had one top priority: to capture an intact Me-262 aircraft with its engines. Dozens of Me-262s had already been shot down, but most were completely destroyed upon impact. The few salvaged engine parts were heavily damaged, providing only limited insights. On March 28, 1945, the breakthrough came. At Lechfeld Air Base in Bavaria, German ground troops surrendered without a fight, and American soldiers found 14 nearly intact Me-262 aircraft in the hangars. Colonel Harold Watson, head of Operation Lusty team, a special unit to capture German aviation technology, could hardly believe his luck. In his official report from April 1, 1945, he wrote, "We have hit the intelligence jackpot. 14 complete Me-262 aircraft with Jumo 004 engines." Some with less than 50 hours total time. Engines appear to be in excellent condition. This is more valuable than 1,000 prisoners. In fact, it was priceless. Within 48 hours, the Me-262s were disassembled, packed, and airlifted to Wright Field in Dayton, Ohio. Hundreds of American and British engineers were already waiting there, eager to unlock the secrets of German engine technology. But Operation Lusty was only the beginning. In the chaotic final weeks of the war, Allied troops systematically seized every piece of German aviation technology they could find. The Junkers factory in Dessau was taken by Soviet troops, who immediately dismantled the entire production facility and shipped it to Moscow. The British captured the BMW plant in Munich, where they found the rival BMW 003 engine. The Americans secured the Messerschmitt factory in Augsburg, along with tons of technical drawings, test reports, and development documents. Most importantly was April 19, 1945. On that day, German troops surrendered in Nordhausen, Thuringia, and American soldiers entered the underground Mittelwerk, where V-2 rockets were being produced. But in a side section of the vast tunnel complex, they discovered something at least as valuable, the complete technical archive of Junkers Motorenbau. 127 metal cabinets filled with blueprints, calculations, material specifications, test data, production instructions, and patent documents for the Jumo 004 and all its variants. It was the complete knowledge base of German jet engine development. 5 years of intensive research and development, now in American hands. Captain Robert Kempel, the technical intelligence officer in charge, wired Washington that very day. Have secured complete Junkers jet engine documentation. Estimate value at several $1 billion in development time saved. Recommend immediate classification and transfer to Wright Field and British counterparts. The document, which became known as Technical Intelligence Report 432, was transmitted to England in May 1945. Just 3 days later, Stanley Hooker sat in his office at Rolls-Royce in Derby, studying the German blueprints. Spread out before him were the complete design plans for the hollow turbine blades, including all the cooling channel geometries, bore diameters, airflow calculations, and manufacturing processes. It was all there. 5 years of German engineering presented on a silver platter. Hooker wrote in a letter to his superior, Sir Ernest Hives, on July 3, 1945, now archived in the Rolls-Royce Company records. The German hollow blade design is remarkably elegant and solves the temperature problem we've been struggling with for 3 years. I recommend we adopt this approach immediately for our next generation engines. Frankly speaking, Ernest, we are not inventing anything new here. We are copying German solutions that already work perfectly. With that documentation, we could have a new engine flying within 18 months instead of 5 years. Sir Hives replied the next day with a single sentence: "Do it, but ensure no public mention of German origins." The work began immediately. Rolls-Royce had already been working on a new engine since 1943, the Nene. The original design used a centrifugal compressor and solid turbine blades, cooled by external airflow. Now, with access to the German data, the design was completely overhauled. The hollow turbine blades were adopted, virtually identical to the German ones in geometry and cooling strategy. The combustion chamber geometry was adjusted to reflect the German annular design. Even details like the fuel injectors and bearing arrangement showed unmistakable German influences. The Rolls-Royce Nene, which first ran in October 1945, was in many ways an enlarged, refined version of the German Jumo 004. It produced 5,000 pounds of thrust, about 2.5 times more than the German engine, But that was mainly due to the larger size and the availability of better materials. The fundamental technological principles, the core ideas that made the engine work, were German. The Nene became a gigantic success. Between 1947 and 1956, over 4,500 Nene engines were produced and used in dozens of different aircraft types. The British de Havilland Vampire, the Hawker Seahawk, the Supermarine Attacker, all flew with the Nene. Even more important was the export. The Soviet Union licensed the Nene in 1946, copied it as the Klimov RD-45, and used it for the MiG-15, one of the most successful fighter planes in history, with over 12,000 produced. The US developed the Pratt & Whitney J-42, a licensed copy of the Nene, which flew in the Grumman F-9F Panther. Even China produced a version. In total, more than 30,000 aircraft worldwide flew with the Rolls-Royce Nene or its derivatives. And every single one of these engines was based on German technology that had been captured in 1945. Rolls-Royce earned hundreds of millions of pounds from engine sales and royalties. Anselm Franz, the man who invented the key technology, received nothing. Franz had a different fate. In May 1945, he was arrested by American troops in Dessau. After 3 months of interrogation in a U.S. internment camp, he was brought to the USA as part of Operation Paperclip. Between 1945 and 1948, Franz worked as a technical consultant for Wright Aeronautical and later General Electric, where he helped to develop American jet engines. But it wasn't consulting in the true sense of the word. In interrogation transcripts released in 1972, Franz described the condition as technical interrogation under duress. He was forced to reveal every detail of his work on the Jumo 04, to explain every calculation, to demonstrate every manufacturing process. The Americans didn't just want the technology, they wanted the knowledge of how to further develop it. Franz initially complied, hoping to later receive employment or at least recognition for his work. This never came. In 1948, his contract was not renewed, and Franz returned to Germany. He found work as a simple design engineer at a small mechanical engineering company in Stuttgart, far removed from the aviation industry. In an interview with the German magazine Der Spiegel in 1969, 4 years before his death, Franz said, "I see my hollow turbine blades in every modern jet engine, every airliner, every fighter jet, even industrial turbines use my invention. But my name is nowhere to be found. History says Rolls-Royce invented it. That's a lie, but it's a lie that no one wants to correct." Franz died on March 18, 1973, in Stuttgart, forgotten by the world he had revolutionized. The Jumo 04 technology spread like wildfire through the post-war aviation industry. In the US, General Electric developed the J-47 engine, the first American axial flow engine to go into mass production. The J-47 showed clear influences of the Jumo 004 design, including the hollow turbine blades and the multi-stage axial compressor architecture. Between 1948 and 1956, an unbelievable 35,000 J-47 engines were produced, flying in the F-86 Sabre, the B-47 Stratojet, and many other aircraft. Pratt & Whitney followed with the J-57, the first turbofan engine, which also used hollow turbine blades based on the German design. In the Soviet Union, the Tumansky Design Bureau developed the R-11 engine, which flew in the MiG-21, one of the most widely produced fighter aircraft of all time, with over 11,000 examples. This engine also used hollow, internally cooled turbine blades. In France, Snecma developed the Atar engine for the Mirage series. Again, with German cooling technology, Britain remained a leader with Rolls-Royce, who developed a whole series of successful engines. From the Avon to the Spey to the RB211, all based on principles originally demonstrated in the Jumo 004. But the true revolution came in civil aviation. In the 1960s, the age of jet airliners began. The Boeing 707, the Douglas DC-8, the Convair 880, all flew with jet engines that used hollow, internally cooled turbine blades. This technology was absolutely pivotal. Modern turbine engines operate at turbine entry temperatures exceeding 2,900 degrees Fahrenheit, well above the melting point of most metals. Without internal cooling, it would be physically impossible to build an efficient jet engine. Anselm Franz's innovation from 1940 is found in every single commercial jet engine today. The Boeing 737, the most successful commercial airliner of all time, with over 11,000 built, flies with CFM56 engines. These engines have turbine blades with internal cooling channels, a direct evolution of Franz's original design, the Airbus A380. The largest passenger plane in the world uses Rolls-Royce Trent 900 or Engine Alliance GP7200 engines. Both have hollow turbine blades with extremely complex internal cooling geometries. But the fundamental principle is identical to what Franz invented in 1940. Every year, more than 4 billion passengers fly in planes, whose engines are based on German engineering from 1940. The economic significance is almost impossible to grasp. The global aviation industry generates roughly 2.7 trillion in revenue annually. A significant portion of that would be impossible without the technology that German engineers developed during World War II. The technical evolution is remarkable. Modern turbine blades are orders of magnitude more complex than Franz's original design, but they follow the same principles. A turbine blade for a modern General Electric GE9X engine, which powers the new Boeing 777X, has over 3,000 internal cooling channels, some of them only 0.2 millimeters in diameter. The blade is a marvel of precision casting, made from a single crystal nickel alloy, a material that has no grain boundaries, and therefore can withstand extreme temperatures better. But the fundamental approach of routing cold air through the interior and letting it escape through tiny holes is exactly the same as in Franz's Jumo 04 from 1940. The engine manufacturers have refined the technology, optimized it, improved it with state-of-the-art materials and manufacturing processes, but they haven't invented anything fundamentally new. They are building on a German foundation. If you appreciate these technical truths, you can directly support the channel with YouTube's Super Thanks feature. This story isn't just historically relevant, it's part of our technological present. Every time you step onto an airplane, you're entrusting your life to German engineering from 1940. The hollow turbine blades that Anselm Franz invented are spinning in the engines beneath your wings. But this story is almost forgotten. Textbooks mention Rolls-Royce, General Electric, Pratt and Whitney as pioneers. Franz's name rarely appears. With your support through Super Thanks, I can dig deeper into archives, interview the last living eyewitnesses, digitize rare technical documents. Every Super Thanks helps me preserve this forgotten story of German technology and show a new generation who truly enabled the jet age. The moral dimension of this story is complex. The Allies won the war against a criminal regime that committed crimes against humanity on an unimaginable scale. The seizure of German technology was justified from the victor's perspective, as reparations for the destruction that Germany had caused. But the individual story of Anselm Franz and his engineers raises difficult questions. Franz wasn't a Nazi ideologue. He was an engineer who wanted to solve a technical challenge. His invention was scientific brilliance, not a political statement. After the war, He was forced to give up his knowledge, then brushed aside and forgotten. The companies that made billions with his technology never gave him credit. Is that fair? The question is hard to answer. What is certain? The technical truth should be told. Anselm Franz invented the hollow, internally cooled turbine blade. This invention made modern aviation possible. Without it, there would be no jet airliners, no global mobility as we know it today. That's fact, regardless of politics or morality. In the 1970s and 1980s, as the first detailed historical studies on the development of jet engines were published, some historians and engineers began to recognize the German role. In a technical paper from 1982 entitled The Development of Turbine Cooling, published in the Journal of Engineering for Gas Turbines and Power, the American engineer Dr. Robert Smith wrote, "It must be acknowledged that the fundamental breakthrough in turbine blade cooling was achieved by German engineers during World War II. Specifically, Dr. Anselm Franz and his team at Junkers. All subsequent developments in this field are essentially refinements of their original concept. Modern turbine technology owes an immense debt to this German innovation." A 1989 book by Sir Stanley Hooker himself, titled Not Much of an Engineer, contained a remarkable confession. On page 127, Hooker wrote, "I must be honest. When we examined the captured Jumo 004 engines in 1945, we were astounded. The hollow blade design was years ahead of anything we had considered. We adopted it wholesale for our Nene engine. Looking back, I regret that Dr. Franz never received proper recognition. He was a brilliant engineer who solved one of the most difficult problems in thermodynamics. His work made the jet age possible." That was rare honesty, but it came too late. Franz was already dead, forgotten by a world he had changed. Today, in 2024, an estimated 120,000 commercial flights take place daily worldwide. Every single one uses turbine engines with internally cooled hollow turbine blades. The technology has become so commonplace that hardly anyone thinks about it. Engineering students learn about turbine cooling in their thermodynamics courses, but most textbooks don't mention where the idea originally came from. One exception is the standard work Gas Turbine Theory by H. Cohen, G.F.C. Rogers, and H.I.H. Saravanamuttu, now in its 7th edition, on page 234. There is a short section. The concept of internal cooling of turbine blades was first successfully implemented by Dr. Anselm Franz in the German Jumo 004 engine in 1940 to 1942. This represented a fundamental breakthrough that enabled all subsequent high-temperature turbine development. It's 2 sentences in a 450-page textbook, but its recognition, its truth. The economic figures are astonishing. Since 1945, it's estimated that over 5 million jet engines have been produced worldwide for both military and civilian applications, and virtually every single one of them utilizes internally cooled turbine blades. The total value of these engines over 75 years, adjusted for inflation, amounts to several $1 trillion. Rolls-Royce, General Electric, Pratt & Whitney, Safran, all the major engine manufacturers, have earned hundreds of billions. If Anselm Franz had held a patent on his invention and received just 1% royalty, his fortune would have been in the tens of billions. But German patents were annulled by the Allies in 1945 and declared public domain. Companies were free to use it without paying. Franz received nothing. He passed away in 1973 in a small apartment in Stuttgart. His monthly retirement income amounted to about $400. In the same week, Rolls-Royce signed a $280 million contract for RB211 engines, whose turbine blades used Franz's principle. The story of the Jumo 004 is more than just the story of an engine. It's the story of how technological progress works, how ideas spread, how innovation is rewarded or forgotten. Franz and his team worked under extreme conditions, with limited resources, under the pressure of a totalitarian regime in a terrible war. Despite that, they created something fundamentally new, a solution to a problem that had stumped the best engineers in the world. After the war, their work was seized, copied, commercialized. They received no recognition, no payment, no gratitude. Is that the inevitable nature of war and technology? Maybe, but at the very least, we can tell the truth. We can say who really invented the hollow turbine blade. We can give Anselm Franz the place in history that he deserves. The technical details are important because they make the story real. It's not just a vague claim that German technology was advanced. It's specific. An 8-stage axial compressor with a 3.14:1 compression ratio. Turbine blades with 0.4 millimeter cooling holes and internal channels. Chromium steel with 13% chromium. 900 kilograms of thrust at 720 kilograms of weight. 1.08 kilograms per kilogram of thrust per hour specific consumption. These aren't myths or exaggerations. These are documented facts from technical reports, test data, and historical records. And these facts show something extraordinary. In 1942, during the worst conflict in human history, a small group of German engineers created a technology that 3 generations later is still the basis of our global aviation. That's the power of German engineering. That's Prussian precision. That's a legacy that we should never forget. Which technical detail of the Jumo 004 impressed you the most? Was it the hollow turbine blades with their microscopic cooling channels? The 8-stage compressor architecture? The fact that Germany produced the world's first mass-produced jet engine, while under massive bombing attacks? Many engineers here in the comments have shared incredible connections. Grandfathers who worked at Junkers in Dessau, original technical drawings found in company archives, modern turbine blades that look almost identical to Franz's 1940 design under a microscope. Every comment adds another piece to the puzzle. Share your thoughts, your knowledge, your family stories about the Jumo 04. Together, we can preserve the true story of German engineering.